there is, in thinking about the nitrogen cycle we saw last Tuesday, that there are basically natural sources of nitrogen fixation, getting nitrogen out of the atmosphere and putting it into living biological systems into the nitrogen cycle. So we saw this the one process of nitrogen fixation, in which bacteria and plants form a symbiotic relationship in order to convert atmospheric nitrogen into usable forms of nitrogen for plants, biologically active nitrogen in the form of ammonia or nitrate. And then we also saw that lightning, because it's incredibly, contains a lot of energy, it's able to split those nitrogen bonds, and when those nitrogen bonds basically break, they're able to combine with oxygen and basically bring down into the system as nitrates. Also biologically active. So if we look at the total amount of natural or background nitrogen sort of moving into the global nitrogen cycle, we'd see that it would account for basically this amount of the graph, about 113 or so teragrams of nitrogen per year. Now, humans have been able to add nitrogen to the global nitrogen cycle, basically convert atmospheric nitrogen into biologically active nitrogen, through three methods. The first one we've been doing for a very long time. By planting nitrogen-fixing plants like soybeans, like peanuts, we've been able to help fertilize soils using plants that are able, and microbes that are able to fix nitrogen on their own. And so if you were to look at just the human activity of using nitrogen-fixing crops or nitrogen-fixing plants, we see that we've been able to increase the amount of biologically active nitrogen a little bit more. So that's going to be represented here in this graph on the screen. So we've gone from about 113 up to about 125 teragrams per year, just through the use of nitrogen-fixing crops. So this is sort of back around 1870, 1880 on our graph. Beginning in the 1920s, the 1920s, we invented chemical fertilizers. The idea of adding fertilizer to your lawn was something that prior to the 1920s, if you wanted to add nitrogen fertilizer to your lawn, you needed manure in order to do so. Chemical fertilizers were something that were invented in the 20s using the Haber-Bosch process, not terribly important, but basically using a highly energy-intensive process to convert atmospheric nitrogen into ammonia that could then be used to create fertilizers today. And we see basically once those synthetic fertilizers come along, the amount of atmospheric nitrogen entering the active nitrogen cycle gone from very low, actually it's ended up contributing a pretty significant amount of biologically active nitrogen, and it continues to grow exponentially. The third little slice up here, shown in gray, represents nitrogen additions through the combustion of fossil fuels. So burning fossil fuels ends up reducing nitrates, another biologically active form of nitrogen. And so over time, we've gone from sort of even back sort of before the Industrial Revolution, through the use of nitrogen-fixing crops, we already augmented the system a little bit. But then beginning around 1950, we see this exponential growth in the amount of biologically active nitrogen entering ecosystems. So now human sources of biologically active nitrogen are just about a little bit more than what we're seeing added on an annual basis through natural processes. So basically, we've taken the global nitrogen cycle and basically doubled the amount of biologically active nitrogen available. Also be worth pointing out that the process of denitrification, it was like way back on Tuesday, but denitrification is the process by which biologically active nitrogen is converted back into atmospheric nitrogen. The process of denitrification has not balanced all these additions. So the amount of biologically active nitrogen in the global ecosystem has been increasing exponentially over the last 7 years or so. So one of the consequences of excess nitrogen is, like phosphorus, this ends up getting leached out of natural ecosystems. It ends up in streams, also causing algae blooms and other types of harmful effects of water ecosystems. Terrestrial ecosystems too, but that's a whole other story we won't get into. One of the consequences associated with all this excess nitrogen is a phenomenon called dead zones, the creation of dead zones. I've got a short abstract here. What exactly is a dead zone in the context of biologically active nitrogen?
Part of the marine ecosystem that has a bunch of dead stuff at the bottom from having too much nitrogen in it. It's nitrogen or phosphorus.
It's in marine systems, it's nitrogen.
Having too much nitrogen, so all this bunch of algae grows and then it all dies. A bunch of dead stuff at the bottom, and as it uses up all the oxygen.
Right, so the key there is not that we just have a bunch of dead stuff at the bottom, but the decomposition of those dead algae ends up creating hypoxic conditions or oxygen poor conditions through the entire water column. And sometimes it's easy to forget that marine organisms also need oxygen to live. And when the oxygen is basically sucked out of the water, there's no longer a habitable place for those organisms to live. So essentially what happens, the way hypoxic conditions develop, and I think you described it very well. You can sort of start off with a stream or a river, and we have excess nitrates moving into that stream or river, and we know how that happens. Is usually associated with major precipitation events, bringing more than we would normally expect of water into those systems. Because there's an increase in nitrates moving into those systems, the algae that already live there are thrilled because now there is an opportunity for very rapid growth. They end up growing very rapidly. The water ends up becoming rather cloudy, some green, foggy, soupy sort of look. And a lot of those plants end up dying from a lack of sunlight, and algae dying. And those bacteria that end up decomposing the algae end up using up oxygen in the process of decomposition. Because those bacteria are undergoing respiration and eating dead material, using oxygen, expiring carbon dioxide, and using up the oxygen available in water. As a result, as that oxygen level drops and drops and drops, the fish, the other invertebrates that need that oxygen to survive, either end up moving elsewhere or dying in place. And when they die in place, decomposers start decomposing them, and the oxygen level keeps dropping until even those bacteria are unable to get enough oxygen from the water themselves. So there's another abstract. We can basically pull some information out of this in terms of how would we understand hypoxia and hypoxic conditions in a qualitative sense. We can verbally describe it. But how would we go out and actually physically make a measure of that water, call it hypoxic or not hypoxic? So I think this abstract sort of gives us an indication. And it also helps describe some of the trends that are associated with hypoxic conditions in marine ecosystems. So give it a read and let's see. Let's see what this tells us. Where are we going to draw the line on hypoxic versus non-hypoxic?
Oh, I hadn't actually gotten that far.
We'll get that far, and then I'll ask you again.
I did the answer, but I couldn't remember the units. 2 milligrams oxygen per liter of water. It's hard to see that.
So when we're above 2 milligrams per liter, we're not hypoxic, but below 2 milligrams per liter, we're in hypoxic conditions. And why is 2 milligrams per liter chosen?
Once you get below that, you start getting into the large.
Yeah, basically that becomes a sublethal and lethal dose of oxygen levels. So it's really taking you and putting you on the top of Mount Everest with that oxygen tank. You know, even if you were nice and warm and toasty, you're going to get all hypoxic. It's not going to be good. And I'm going to get soup putting up there. You're not going to be able to get enough oxygen in the ability to survive. Now, what's been happening with marine ecosystems over time in terms of where hypoxic conditions have been found? Is it steady? Is it decreasing? Is it increasing? If it's increasing, is it increasing linearly, logarithmically, exponentially? Going up. How do you know?
Those bars on the right are much taller.
All right, and what's on the x-axis?
X-axis is like spheres.
Okay, so that's time. So it's going back to 1916 and up to the year 2006. And what's on the y-axis? What's our response variable?
Number of hypoxic.
All right. So it's not necessarily area, but it's giving us an indication as to how many sites are affected by hypoxic conditions. Now, why do you think there's this exponential growth? There's two answers to this. There's two answers.
Perhaps it creates a feed-forward loop that where there's a little bit of nitrogen now that there's this, something will happen that can create even more nitrogen in the water.
Right, so that will actually, since we're not looking at the area affected, we're looking at the number of sites affected, the number of different locations. I think you're absolutely correct, but that's not going to give us an answer to this particular question.
All right.
All right? So you're wrong, but for the right reason. Yes?
So, like, industry is more global, of like, the further we get along the way. So I was thinking if there's more industry and if it's in more places, then like the runoff that you create from industry, especially in places with less, regulation, as we do in this country, you would have more.
Okay. Absolutely. So eutrophication can be a response of sort of our expanding industrial footprint globally, so that as we have more industry, more locations, we end up getting more and more sites affected by eutrophication. Second, yeah.
Typical HERS population is increasing a lot, so our needs are increasing as well. So the kind of fossil fuels we use, the food we consume, so the food we consume is requiring more fields.
Okay.
And so more fields is allowing more runoff of nitrogen to go into the actual water itself. And then the more phosphorus that we use, the more nitrogen that comes from acid rain into the water.
All right. Excellent. So both good examples. There's a third one, which is a little bit more subtle. but it's worth thinking about. Now, if you think back to the 1920s, 1930s, there were very few sites being detected. If you go back and read ecology stuff or other science stuff in that period, there's not a lot of information out there about hypoxic marine ecosystems. They were very highly localized and not considered a wide problem. It was just sort of a unique problem known to just a few locations. However, basically beginning in the 70s, as this began to ramp up, people began looking at more and more locations and finding hypoxic conditions in more and more locations. So part of this was this increase, and again, this big jump in the year 2000, was that scientists they were more acute into this and began looking for it a lot more aggressively than they had back in the 20s, 30s, 40s, and 50s. So part of this is just the fact that we're monitoring it more aggressively and therefore finding more sites that are affected by hypoxic conditions. My guess is this is not as rapid a jump as it appears. It's probably a smooth jump. We're missing a lot of sites that were affected down here that we just didn't know about. So if we were to look across the globe and see where these hypoxic sites are occurring, we've got this sort of color-coded to 3 colors. The yellow sites indicate eutrophic conditions, so they're nutrient enriched, and sort of moving towards hypoxic, but not quite there yet. The red circles represent hypoxic conditions, so representing sort of dead zone areas. And the green, God bless the green, these are systems that had been hypoxic or had been eutrophic in the past, but are actually moving the other direction. They're getting cleaner over time due to direct intervention. So what's the general trend? How would you describe to a friend sort of this phenomenon of marine dead zones?
Looks rather coastal to me.
Well, it's going to be coastal because that's where the water meets the sea.
They're more concentrated in industrialized areas.
All right, so they're in Japan, Eastern China, Eastern U.S., Western U.S., Brazil, South Africa, Australia, a little bit in Africa, a little bit in India. Where are the recovery sites concentrated? So developed countries, so Europe and the U.S. Mostly Europe. Yes.
What's the difference between, and maybe I missed this, but what's the difference between hypoxic and eutrophic? And like, are they not synonymous?
They're not synonymous. Eutrophic indicates that conditions are nutrient enriched, and it is a form of pollution, but it's not to the point that has created those hypoxic conditions. So we're still at 3 or 4 milligrams of oxygen per liter of water and declining, but we haven't hit that threshold yet.
Okay, and once someone, okay.
Yep. Excellent. Great question.
There's a dot in Antarctica down there.
Yeah. Which is recovered. I don't know what's happening there. So there are a number of approaches to try to restore systems that are eutrophic or systems that are hypoxic. And one of the approaches that's been sort of a promising approach, but not fully tested out, is actually using organisms as filter feeder organisms in marine systems to try to filter out the nutrients and try to restore water quality. So I love the title of this paper because you know exactly what this paper is going to be about, what the study is going to be about, just for reading the title. The unfortunate part is you have to read the darn abstract to get the answer. remember our rules, we wanna go through that abstract first and figure out the words that we don't know the meaning of. We wanna get those all clarified. What?
Just read the lesson.